Righty. So I'll begin then, and thank you very much for the invitation. It's been a couple years since I have been to Montreal, and I'm very happy to have this opportunity to visit it, sort of virtually. Okay, so now what I want to do is I assume that most people in the audience have some expertise in spectral asymptotics. And I've sort of learned that that's rarer and rarer as time goes on. But I'm going to assume that you know spectral asymptotics on compact Riemannian manifolds, such things as Weyl's law and the Gutzwiller Deutsch-Gilliman trace formula. The purpose of this project with Alex Strohmeyer is that we were just questioning, like, these theorems on spectral asymptotics are cornerstones of non-relativistic quantum mechanics. So what is their relativistic generalization? You could interpret that to mean things, sort of Weyl laws and so forth for the Dirac equation, but most people use the elliptic one. So we want to generalize spectral asymptotics to a curved space-time, general relativity. So in effect, what we're going to do is give a framework for generalizing essentially any theorem on spectral asymptotics for the Laplace operator or a semi-classical Schrodinger operator on a compact manifold to a stationary space-time, to a general relativistic setting. So I'm sort of assuming everybody here is familiar with spectral asymptotics, but not with general relativity. Okay, so in this slide, I'm just repeating what I just said in a somewhat different way. You know, the Weyl law, we use the propagator. I forgot to put the T in here, but we use the propagator, and that's clearly non-relativistic because it involves a distinguished time variable. So the question is, how can you do spectral asymptotics in the relativistic setting? So in order to separate out the main ideas from the techniques, those who are very familiar with Fourier integral operators and spectral asymptotics will not find that the techniques are particularly new. There are just some things that are new involving propagators in general relativistic settings. But much of the proof is very similar to Deutsch-Gilliman. It's really more setting up the right framework for doing it that's different. So we're going to do spectral asymptotics on globally hyperbolic stationary spacetimes. So I'll spend some time explaining what that means. For convenience or technical simplicity, we're going to assume that the space-like directions are compact, that you have a compact Cauchy hypersurface. So we plan on moving away from that assumption, but even if you do spectral asymptotics, you know there's a world of difference between working on a compact Riemannian manifold and working on an infinite volume Riemannian manifold. There's a world of difference between them. So you're going to expect it to find it here. So when we have a compact Cauchy hypersurface, we're going to prove a Weyl law and a Gutzwiller Deutsch-Gilliman singularity trace formula. The second result is new, and it's sort of one of those things which is formally obvious to people who work in spectral asymptotics and seemingly unheard of in the physics literature. Namely, we're just going to look at the Klein-Gordon operator with a mass term in it, and we're going to observe that the mass term behaves like a Planck constant, and we're going to study the semi-classical asymptotics using the inverse mass as a Planck constant. So I'll get to that later, but it's a kind of curious application of the theory that I have not yet met a physicist who ever thought about this. Perhaps somebody in the audience has seen this before, but it's very natural from a mathematical point of view. So in future generalizations, Strohmeyer and I plan to study situations where the space-like directions are non-compact infinite volume, such as the ones where you do scattering theory on Rn, or where you have a black hole. So there are quite a lot of different generalizations you can study. So, and the key points are like this. When you do the Deutschmann-Gilliman trace formula, you are trying to, you use basic quantization. You have a compact Riemannian manifold. You have a phase space, that's the cotangent bundle. You quantize it to get L2 of the manifold. And then what we do is we study the relations between the eigenvalues and eigenfunctions of the Laplacian and the dynamics of the geodesic flow. So when we generalize to Lorentzian manifolds, to curved spacetimes, we have to figure out what's the phase space? What's the Hilbert space? What dynamical system are we supposed to be interested in? You might think that the obvious thing to do when you have a Lorentzian manifold is that the cotangent bundle of the manifold, that should still be the phase space perhaps. L2 of the manifold, that should be the Hilbert space. That's not at all what we're going to do. And what we're going to do is completely incomparable and singular with respect to that idea. So instead, the phase space is going to be the space of null geodesics of the space-time. So we have to explain why that is a phase space, meaning symplectic manifold. Second of all, the quantization of that phase space is not L2 of the space-time. It's a Hilbert space of null solutions of the wave operator, solutions of Baksh equals 0 with a certain inner product on it. So if you're into general relativity, you will have known that since about 1960s, Penrose has been studying the space of null geodesics. And in any quantum field theory book, they will study the null solutions of Baksh, and they will talk about quantization on a curved spacetime in terms of positive frequency solutions of the wave equation. So this ties in with those types of papers. Now I want to start by reminding what happens on a compact Riemannian manifold. I want to make it seem sort of obvious how the generalization we're aiming at works. So on a compact Riemannian manifold sigma of any dimension with metric h, we study the Laplace operator and the wave group. There are two different ways to study the wave group. You can study this 2x2 matrix wave group, which I call U of t, or you can study this scalar V of t. U of t has the advantage that we only have even functions of the square root of Laplacian appearing in the matrix. So these are very elementary, first studied by Hadamard. V of t involves the square root of minus Laplacian, which is a pseudo-differential operator. And these were first studied by, to my knowledge, by Hermann or Deutschmann-Gilliman in the 60s and early 70s. So, of course, I'm going to use the notation that the lambda j's are eigenvalues of the square root of minus Laplacian, not eigenvalues of the Laplacian. Okay, so that's the propagator in non-relativistic quantum mechanics, or for the wave group. The wave trace is the trace of the wave group, and that's a tempered distribution. So if I use the matrix, I get the cosines. For some things, there's advantages in using the half wave group, V of t, just trace of e to the it root Laplacian, and then you get these summations of e to the it lambda j, that the beauty of that is that it's the boundary value of a holomorphic function in the upper half plane. So it was discovered by Gutzwiller and Balian Bloch, and later proved as a rigorous theorem by Colin-Verrier, Chazarin, Doistermat, Gilliman, that these tempered distributions have singularities only when t equals 0 or t is the length of a closed geodesic. I'm pretty sure this is familiar ground to many people here. The leading order singularity is like t to the minus dimension plus 1. And using that singularity in Fourier-Tauberian theorems, you can derive the Weyl law. So, okay, so the Weyl law counts the number of eigenvalues of the square root of Laplacian less than or equal to lambda. You get the volume of the manifold times lambda to the dimension plus lower order terms. So trace of the wave group is the Fourier transform of the derivative of n of lambda. And Fourier-Tauberian theory is all based on the relations between n of lambda and the Fourier transform of its derivative, which is the trace of the wave group. So this is just a very quick recollection that the trace of the wave group has singularities at lengths of closed geodesics. At a particular length, if you have a non-degenerate closed geodesic, then you get just t minus the length inverse. That's the kind of singularity. And it has a leading order coefficient, which has symplectic information about the geodesic flow around the closed geodesic. So it's either the I pi over 4 times the Morse index. I somehow left the Morse index out. And then you have the primitive period. And in the denominator, you have the determinant of 1 minus the Planck array map. So because this time is limited, I'm not going to review all these definitions, but the Planck array map, it's the derivative of the first return map around in a little symplectic cross section next to the geodesic flow. So in any case, this is the basis for all inverse spectral theory of the Laplace operator, or these spectral invariants. Now, what is the relativistic generalization? Well, we want to prove those types of theorems for globally hyperbolic spacetimes. Globally hyperbolic means it has a Cauchy hypersurface. It means that every time-like or null geodesic crosses the surface exactly once. It's like a cross section to the null geodesic or time-like geodesic flow. The wave equation is well posed. On a globally hyperbolic spacetime, it's not well posed otherwise. So almost everybody in general relativity assumes you're dealing with a globally hyperbolic spacetime. We're going to make the assumption that the space-like cross-section is compact, and that's easy to understand. We're also going to assume that the space-time is stationary. So that's a crucial definition. It's made in almost all texts on quantum field theory on curved space-times. It's really not understood how to do quantum field theory if you don't have a stationary space-time, for reasons that will become apparent. So stationary means that you have a time-like killing vector field, z, something like d by dt. So in other words, the flow of the flow of a killing vector field is by isometries, and it's time-like, which means that the isometries are sort of time translations. They're moving you forward in time. And in a sense, but you have to be very careful about the sense, it's sort of saying that the universe is not really changing its geometry in time. But you have to interpret that, because what we think of as our world is the Cauchy hypersurface. That's what we experience. But different observers experience different Cauchy hypersurfaces. There's no unique choice in this setting of a Cauchy hypersurface. So that's the relativistic part. So the key definition is that the wave group is actually going to be the killing flow. And we'll see why that's natural. Time translations will be our wave group. So we have to understand why that works that way. We don't look at the killing flow acting on L2 of the spacetime. We look at the killing flow acting on null solutions of the wave equation. So this is a picture of a globally hyperbolic spacetime. The green things are Cauchy hypersurfaces. And so there are 4 Cauchy hypersurfaces which are drawn in. It's called sigma sub t. There's no best choice of a Cauchy hypersurface. If the space-time is called static, then there is, but in general, there is no best choice. So if you do everything by making a choice of Cauchy hypersurface, you break relativistic invariance and you end up with a hard to interpret mess. So in relativity theory, you want to maintain relativistic invariance in what you do. Okay, so what is our relativistic quantum mechanics? In place of L, so instead of using L2 of the whole space-time, you know, in some sense, we're looking at L2 of the Cauchy hypersurface. That would be a better model for what we're doing. But that's not relativistically invariant. And in place of that, we're using the kernel of the wave operator. And we need to endow it with the Hilbert space inner product. And we want our inner product to be relativistically invariant. Otherwise, the results we have depend on what choices you made of Cauchy hypersurface or observer, and we don't want that. As I mentioned earlier, the cotangent bundle of a Cauchy hypersurface is a kind of model for the phase space, but to make it relativistically invariant, we're looking at the symplectic manifold of null-geodesics of the space-time. These are geodesics whose tangent vectors are light-like, which means that the Lorentzian inner product of the tangent vector with itself is 0. In some sense, geometric quantization tells you that to every symplectic manifold, there is a Hilbert space. Here, the symplectic manifold is the space of null geodesics. The natural Hilbert space associated to null geodesics are null solutions of the wave equation. Despite the fact that I find this completely obvious, we haven't been very successful in tracking down this interpretation in the physics literature. The closest thing we come is to the articles of Penrose, but they have not been followed up, even though he wrote them in the 60s. Now, to understand why it's natural to think of the time translations as like a wave group, let's just do the whole thing that we're doing in the product setting. That means we're just going to look at a Riemannian manifold cross R with a trivial product metric minus dt squared plus h. H is the Riemannian metric on sigma. Incidentally, feel free to ask questions. So this is called ultrastatic in the relativity literature, but I think it's easier for everybody if I call it product. So as we know from teaching undergraduate courses in Fourier analysis, you get solutions of the wave equation by taking eigenfunctions of the Laplacian, phi j of x, and multiplying by e to the plus or minus it lambda j, where the lambda j are the eigenvalues of the square root of the Laplacian. So these are null solutions of the wave operator, which is d squared by dt squared minus the Laplacian. So here's the obvious observation that the eigenvalue, the frequency lambda j, the eigenvalue of square root of Laplacian on phi j is the same as the eigenvalue of 1 over I d by dt on the solution, on the null solution uj. So that suggests, and we can think about, the trace of the wave group as just a trace of time translations acting on these null solutions. So, you know, you can then think to yourself, I want to find an inner product on the space of null solutions so that the uj form an orthonormal basis. Okay. Obviously, the UJs are obviously not in L2 of the whole space-time because of the e to the IT lambda j factor. So that's what we did. So now let's look at what a globally hyperbolic stationary space-time is. All of these globally hyperbolic spacetimes look like R cross a Cauchy hypersurface. It's just that there's no unique or particularly good way of choosing it. There is an invariant way of understanding what a globally hyperbolic spacetime is. Actually, I don't want to explain it for lack of time, but so we're going to look at this model, and then the metric has this kind of complicated form. There's a function n in front of n squared in front of dt squared. That's called the lapse function of the space-time. Then a little hij is my notation for a Riemannian metric on the Cauchy hypersurface. And then there's an additional one form called beta, which is called the shift one form or vector field. So beta is independent of t, and hij is independent of t. Beta is like a one form on the cross section. It depends on what cross section you pick. It's really a connection for an R bundle over the space of Killing orbits. The lapse function is independent of t. All of these functions, n, h, and beta, depend on your Cauchy hypersurface. So the Killing vector field is just d by dt, because the coefficients n, h, and beta are independent of t. All right. What classical dynamics do we want to study? What's the analog of the geodesic flow? Well, that's sort of complicated. So when we talk about the space of null geodesics, we first of all look at the standard Hamiltonian on space-time, which is very similar to the one if you do in the non-relativistic setting. It's the symbol of the wave operator. So in this line, when I write norm squared, it's really the Lorentzian norm squared. So it's not positive definite. So when we look at null geodesics, first of all, we look at the characteristic variety of the wave operator. This is the zero set of the symbol. That's a bundle of light cones. At every point in space-time, in the cotangent space of the space-time, you have you have a light cone. So it's a light cone bundle. Okay, and it's a level set of the symbol of box. And as a result, the Hamiltonian flow of the symbol of box, which is the bicharacteristic flow or the Lorentzian geodesic flow, the Lorentzian geodesic flow preserves the level sets. So it restricts to the null cone bundle, and the orbits of the geodesic flow in the null cone bundle are the light-like geodesics. These are geodesics where gamma dot, inner product gamma dot is zero. And they're like fundamental in general relativity for various reasons, in particular to Penrose and people following Penrose, because these are conformally invariant. Now, we don't use the characteristic variety of box as a phase space because it is not a symplectic manifold. It is a hypersurface in a symplectic manifold. So we need to divide out by the bad direction, which is the flow lines of the null geodesic flow. And so we take the quotient space of the characteristic variety by the Hamiltonian flow, and we get the space of null geodesics. It is a quotient space. So that's, I write it as calligraphic N. That is the space of null geodesics. And that's a symplectic manifold. It's actually conic, homogeneous, because the characteristic variety is homogeneous. If I multiply C by a positive real number, it's still in there. And the R action did not change that, dividing by the R action. So this is a conic symplectic manifold, which is the kind of place where you do sort of differential operator theory. And so n is going to be our phase space. Let me pause for just a moment. Does anybody have a question? I'm not sure if I'm going too fast or anything like that. Can somebody give me a heads up? Dima?
Steve, how big is the space of the stationary space-times if you look at a fixed, compact cross-section?
Well, let's go up a slide. You have as many, see, topologically, it's just going to be R cross sigma. Okay, and a sigma could be any compact manifold. But in terms of the metric, the parameters are these fields. Capital N is a function, beta is a one form. These are on sigma, and H is a Riemannian metric on sigma.
So can you start with any Riemannian metric on sigma, and you will have a station, and then find n and one forms to get the stationary spacetime?
Yes. I might make one remark. The difficulty with usually with spacetimes is not getting a lot of metrics. There are like lots of metrics around. Usually the difficulty is getting a solution of the Einstein field equations. I'm never talking about that. Just like Deutschmann and Gilliman do not assume they're on a compact Einstein manifold, I'm not assuming that the universe is an Einstein universe either.
I see.
Right?
And so another question, is your theory, does your theory basically depend only on the conformal class?
No, that is actually a good question. When you do massless Klein-Gordon equation, then there's something called the conformal one, and the null space is preserved as long as you're conformally stationary. You don't even have to be stationary. But as Alex has explained to me,
just a second.
Somebody should shut their audio off.
Sorry,
Alexander, say Sasha. Sasha, turn off your audio. Turn off your audio.
Okay, I muted.
Right. Yeah. So there's no assumption here. These are any possible spacetimes. There's no assumption about being a solution of the Einstein equations. Those are, of course, important if what you want to understand is what the vacuum universe is like. But anyway, we have matter in our universe. Is that okay?
Yeah.
All right. So now the basic dynamical system is the killing flow on the space of null geodesics. Usually at this point, I try to draw a picture. You might think of a null geodesic as a kind of corkscrew spiraling curve in space-time going up the time axis. It sort of spirals up the time axis. It doesn't have to be exactly like that. Like in Minkowski space, they're like straight lines. But anyway, you can think of them a bit that way. And time translation means that you sort of shift this spiraling curve up in time axis by some number of units, and then it comes back into itself. So that's what a periodic orbit of a killing flow on the space of null geodesics is. So the killing vector field commutes with the box operator because it's isometries. And the Hamiltonian flow of the symbol of z, which is just time translations, e to the tz, that commutes with the geodesic flow. So you can do what's called reduction or symplectic quotient and study the killing flow on the space of null geodesics. So that is our dynamical system. So the way I like to put it is that to every spectral problem, there is a controlling dynamical system. So in the case of elliptic theory, of course, you look at an operator, elliptic operator P, and then you look at the geodesic flow generated by, or the Hamiltonian flow generated by the symbol of P, and that's the controlling flow. That's been known since Hermander or Maslow or whatever. So that controls the growth rate of eigenvalues, and it controls Deutschmann-Gilliman. So here we had to say, like, what's the controlling dynamical system that's going to be controlling the spectrum? So the answer is the killing flow on the space of null geodesics. So the Hamiltonian for this is standard because it's just a vector field. D by z is just like d by dt. It's just a vector field. So the Hamiltonian at a point zeta, meaning x and c, is just to apply the covector to the vector field. And that's how you define a Hamiltonian on the cotangent bundle. So, whoops. So this is just called the Claro integral in general. Whenever you have a vector field generating isometries, it lifts to the cotangent bundle by this formula that you just define H on a covector by letting the covector eat up the vector. And that generates the lift of the flow from the manifold to the cotangent bundle of the manifold. So I think I'd probably have said everything else. One important thing for later on is that because the vector field Z is time-like, this Hamiltonian is positive and homogeneous. Because we're looking only at null geodesics. These are all these C's are null. So we're letting null covectors eat up a time-like vector. So if you want, you could identify, you can make identifications. I think I'm not going to say that right now, but there are ways of identifying this. So periodic orbits just mean that this is the killing flow, and zeta is a null vector, a null geodesic. And if the killing flow translates that null geodesic into itself, then that's a periodic orbit at time capital T. There actually are papers in the physics or the math and physics literature about the killing flow on the space of null geodesics and what its periodic orbits are. Just to make an obvious remark, you might have thought, well, as I mentioned, L2 of the space-time is not our Hilbert space. And our flow is the killing flow on null geodesics. It's not the null bicharacteristic flow. But you might ask yourself, well, what about periodic orbits for the null bicharacteristic flow on space-time? And their answer is there are none, because we're on a globally hyperbolic space-time. So every time-like curve only intersects a Cauchy hypersurface once. You don't have any periodic orbits. So it's quite natural to define it this way. Let me pause for a moment to see if there are any questions. I guess if you have questions, you can send a chat to Dima, and then Dima asks the question. Are there any questions about what I'm doing?
Steve, so once again, in what you are defining, will there be periodic orbits?
What's that?
In the trace formula you're defining, you will have some periodic orbits, right?
Yes. It's pretty complicated to work them out. But there is a paper which worked out sort of what this is like in terms of the Cauchy hypersurface, in terms of the lapse function, the shift vector field, and the Riemannian metric on sigma. If you do that, you don't really understand what it means relativistically, but it sort of looks like a particle that's in a magnetic field determined by the one form, and also subject to an electric field. It's sort of complicated and messy, but you can work out the equations of motion. I suppose if you want to understand the periodic orbits, you might have to choose a Cauchy hypersurface and work it all out. And then it's just like a particle in a magnetic field. Sure, it has periodic orbits. And, you will also, get contributions from N. Does that answer your question?
No, I just wanted in the Riemannian case, we have a lot of intuition, like there are integrable geodesic flows, ergodic geodesic flows, and so on. In the relativistic case, this is much less developed, or what's the story?
Well, it's not developed at all.
I see.
Right, yeah.
So if
So,
you're,
I mean, I would guess that you have, if you have additional killing vector fields on your space-time, like Schwarzschild or Kerr, you have like, it's all completely integrable. All people's favorite black hole models are always completely integrable. So you will have many commuting vector fields, and everything that commutes that's in a killing vector field will pass to the quotients and live on the space of null geodesics. So you will have a integrable Hamiltonian system on the space of null geodesics. No problem.
Okay. So then you will have kind of like an analog of a sphere or a torus or some quantum completely integrable system.
Yes.
Okay.
All righty. Now, what about the wave operator? So the wave operator just looks like the formula for the Laplace operator, except that the metric itself, it has signature -1, 1, 1, 1, whatever. It can be in any dimension. It's a hyperbolic operator, not an elliptic operator. And so that's box. And we could add a potential to box if it's invariant under the killing vector field. And Alex Stromeyer, for example, is adamant about this because physicists like to add in the scalar curvature to make the conformal wave operator, and that uses scalar curvature for V. To date, the only one we really studied in detail is adding a constant. We add box plus m squared. That's called the Klein-Gordon operator. And okay, so we're going to talk about that in a moment. So I think this slide is fairly straightforward. Boom. So we're looking at the spectrum of the killing vector field or differential operator induced by it on the kernel of box. They commute. If we look at the one parameter unitary group generated by 1 over IZ, that is the just killing translations acting on kernel of box. So you can think about them as just operating by pullback on solutions of the wave equation. Or you can think about it that we're studying a pair of commuting operators. So the basic thing is that this is an elliptic system. The box operator is hyperbolic. Of course, it has a continuous spectrum. So, for example, you could have any mass. So we're looking at just the null solutions. And so the dt squared has the wrong sign to be elliptic, but z is basically d by dt. So if we look at this pair of equations, it's like sort of making up for the fact that d by dt has the wrong sign, and it makes this system elliptic. As a result of which, the spectrum consists, the spectrum of dz in the kernel of box basically it's a discrete spectrum of real numbers with no accumulation points. It's a discrete spectrum. It's just very much like the spectrum of square root Laplace operator. So if you operate in a very high level of generality with potentials, you can get some complex eigenvalues, but let's not discuss that because it's really a secondary issue. So the spectrum, the way we define it, symmetric around the origin. If lambda is an eigenvalue, minus lambda is also an eigenvalue. It's elliptic, all the eigenfunctions are smooth. So in some sense, it's just exactly like what we're used to on a compact Riemannian manifold. So let me state the results. Well, the first result is that if I look at the trace of the killing flow on the null space of box, it's exactly like the Deutschmann-Gilliland trace formula on a compact Riemannian manifold. You get a contribution at t equals 0 you get a contribution at the length of every periodic orbit of the Killing flow on the null space of on the null space of box, and the space of null geodesics, I mean. Everything about it looks very similar. Here you see that the leading coefficient is the volume of the set of the volume within the space of null geodesics, where the symbol of z is less than or equal to 1, where this Clairaut integral is less than or equal to 1. So this plays the role of the unit cobalt bundle inside of the space of null geodesics. Obviously, we needed to know the space of null geodesics to pose this problem. All these terms here are homogeneous distributions. So if you're familiar with, the basic theory on a compact Riemannian manifold, the message is it's basically the same, where the space of null geodesics takes the role of the cotangent bundle. What I have not explained here is what I mean by the trace, because I have not yet defined a Hilbert space inner product. But once I define a Hilbert space inner product on the null space of box, that should be null space of box, not car box, null space of box. Once I define an inner product on the null space of box, then it makes sense to define the trace. Let me just pause for a moment to see if any questions have popped up.
Steve, there was a question in the chat. Is there a link to minimal surfaces and good choices of Cauchy hypersurfaces?
No. No, not really. I mean, no. Let me go on from that question. Minimal surfaces arise, for example, when you study positive mass conjecture, things like that, but not in this problem here. It's really the only thing it's really about the eigenvalues. And the only geometry eigenvalues really can see is periodic orbits of some Hamiltonian flow. So what we're trying to do is identify what Hamiltonian flow is it. So, so I apologize for putting car here. This should have been Kerr, not car. So you get a Deutschmann-Gilliman singularity expansion at the periodic orbits of the Killing flow on the null geodesics. It looks just exactly like it. So if the fixed point sets are non-degenerate, you have non-degenerate periodic orbits, then the trace, I should not have put this real part in, sorry. The trace should looks just like it does in the Deutschmann-Gilliman formula, and here's like the leading order term. So, I mean, it looks identical. It's just a matter of figuring out what is T gamma and what's P gamma. So, T gamma is the period. P gamma is the Planck array mat. That makes sense for any Hamiltonian flow. So in particular, we're really looking at the unit vectors. We're looking at the level set of the symbol of Z, the level set of the Clairaut integral. That's like the unit tangent bundle. So we're looking at a symplectic cross-section to the geodesic flow there. We have these periods and we have a Planck array map. So everything just goes along because it was always general about symplectic things. The Morse index is a little subtler. Morse index theory in the Lorentzian spacetime is a very complicated subject. One of Karen Uhlenbeck's earliest papers was about trying to define Morse theory for that. But so I don't really want to go into that here, but you need a Conley-Zander index, and it's a little subject in its own right, Morse theory for geodesics. Okay, so the only message on this slide is that Deutschmann-Gilliman has an exact analog here. And therefore, you get a Weyl law. The Weyl law counts the number of eigenvalues of the Killing vector field in the null space of box. And it grows exactly like the eigenvalues of square root Laplace operator on a compact Riemannian manifold of dimension n, or dimension here n minus 1. I used n for the dimension of the space-time. So n minus 1 is the dimension of the Cauchy hypersurface. So it makes sense that that's the exponent. once again, you get that there's a symplectic volume measure on the space of null geodesics, and we get the leading coefficient is the Liouville measure, if you like, of the unit vectors, where the symbol of z equals 1 in the space of null geodesics.
I have a question.
Let me just, before the question, let me just point out one thing. Namely, if you did not work relativistically invariant, you would have gotten some volume here, which had the capital N, the shift vector field, and everything else in it. How would you even understand what it was? Okay, John, what was about what was
well,
it?
so if Z and the box operator is jointly elliptic, right?
Mm-hmm.
So do you know what the joint eigenfunctions are?
Yes. I mean, yes and no. I mean, do I ever know what they are? Like on any Riemannian manifold, do I know what the eigenfunctions of the Laplacian are?
You know, can you say, well, no, but there, it's an elliptic system, right? So it's QCI. So
it's not QCI. It's not QCI. I just have two
not
commuting operators in dimension n.
Ah, okay, okay, all right.
But you know, like you could do quantum ergodic theory in this setting. There's no I mean, the null, like the killing flow on the space of null geodesics is something or other like a magnetic flow on the cross section. It could be like ergodic, for example.
Yeah, okay.
You could have quantum ergodicity of eigenfunctions. I mean, there's no way you really know what the eigenfunctions are.
Yeah. Okay.
But if the cross section is like a sphere or a torus, does it make things a little simpler or not?
I'm sure it does, but you know, if you just allow a general old H, a general N, a general beta, it's like worse than putting a general magnetic field and a general metric on a torus.
Yeah, no, but in some, suppose you have a round metric on a sphere or something flat on a torus.
Yeah, but
then probably things are slightly easier, no?
Yeah, you could do that. You can. You don't want to go back to product space-time, so you have to make it interesting in some way or another. Mm-hmm. So the question is, how do you want to make it interesting?
Okay. But
so there is a invariant thing. You know, the space of killing orbits also exists as a manifold. That's an invariant way of talking about a cross section, about sigma. It inherits in a natural way a Riemannian metric. And so you could try to decide that to specify that. That's fine. On the other hand, it's not true that that this killing flow in the space of null geodesics is the same as that one. It's not the same as the geodesic flow for that either.
I see. Okay.
It's just it has its own level of complexity. The geometry has been worked out in some papers by general relativists, but not that much. I better move on a little bit.
Okay.
So here's a strange result where we're going to treat the mass as a semi-classical parameter. To my knowledge, nobody's ever done it before. Not that it's difficult to do, but okay. We take the Klein-Gordon operator, box plus m squared. We divide it by m squared, making it m to the minus 2 box plus 1. Well, that m to the minus 2 looks a lot like h squared in front of a Laplacian. So let's run with that and see what we get. And then we're looking at the joint. See here, we're looking at the joint spectrum of the massive Klein-Gordon operator and the killing vector field. And we could study semi-classical asymptotics the way that we do whenever we look at a joint spectrum, which means we look at pairs, mass and the eigenvalues of the killing vector field on massive solutions of the wave equation. Solutions, you know, what they call massive scalar fields in quantum field theory. So we have, for every m, we have a discrete set of eigenvalues, lambda j of m. So so I think in terms of like a two-dimensional lattice, and if you go along, the vertical is m, and the horizontal are the eigenvalues lambda j. Before we fixed m equal to 0, and we went in the horizontal direction. If we fix m and let you can go in the horizontal direction, we get pretty much the same thing for every m, because it's not really a semi-classical parameter if we go in the horizontal direction. If we go along lines with positive slope in the joint spectrum, then we're letting the mass go to infinity as well as the eigenvalue. Both are going to infinity in such a way that the ratio lambda j of m over m tends to a limit, which we call nu. So this is reminiscent of what is called ladder asymptotics in spectral theory and elliptic spectral theory. So we can play this game in the relativistic setting. And Alex is more knowledgeable than I am about quantum field theory on relativistic spacetimes. And we spent some time, more or less, he spent some time trying to figure out what is the physical interpretation of this. So we get a semi-classical Weyl law, very similar to the ones that people prove in semi-classical Schrodinger asymptotics. You fix an interval, and you look at the ratios lambda j of m over m in a very small interval around nu of width 1 over m. Okay, so we want to count that number of eigenvalues. As m tends to infinity, the eigenvalues, the number of them is going to tend to infinity. And we want to understand Weyl asymptotics. And we want to understand how it depends on this constant nu. So first of all, once we, so to speak, tilt the ladder, we change the controlling dynamical system. It's no longer going to be massless geodesics, null geodesics. It's going to be massive geodesics. Time-like geodesics, where the length squared of the geodesic is m, or minus m squared. So instead of looking at this, the space of null geodesics, we look at the space of massive geodesics with a fixed inner product, Lorentzian inner product. Okay, that's like mass hyperboloid. It's like instead of looking at a null cone, you're going to look at a two-sheeted hyperboloid cone, and you're looking at the geodesics lying on the massive hyperboloids rather than the null hyperboloid. So I hope I'm not going too fast. I really can't tell. If you have to slow me down if you want me to slow me down. So here's a slide where it says that the semi-classical symbol of the massive Klein-Gordon operator, it has which I wrote out. I sort of multiplied by m. But if I treat it like a homogeneous pseudo-differential operator with, I mean, a semi-classical pseudo-differential operator, the mass disappears. So everything becomes kind of homogeneous. And we end up with the massive hyperboloid with mass 1. Okay, so that's a little non-obvious that because everything is kind of homogeneous when we do ladder asymptotics, actually it has the effect of fixing the mass at 1 and looking at a two-sheeted mass hyperboloid with mass 1, just like you look at the unit sphere in the cotangent bundle. And the nu comes up as the level set. Now everything is non-homogeneous because you're on a massive hyperboloid. So the level set is the level set of the killing vector field symbol. They're all different now because you're sort of slicing a mass hyperboloid at different levels. So that's the phase space. And we still look at the killing flow on a level set of the symbol of the killing vector field. And that's our controlling dynamical system. And it will change depending on what level set we look at, what value nu we put in there. So these are like different time slices of the mass hyperboloid bundle. So N1 is like massive geodesics of mass 1. It's a little complicated how we work it out. So let me just try to explain in words that the governing dynamical system is the killing flow on the space of mass 1, null-geodesics. So this is the main result in the massive case. We're trying to count the number of these eigenvalues, and we have to. This is sort of like an Ivry type situation because we're counting things in very small intervals. So we have to assume something about the closed orbits having measure 0. I don't want to get into it. I just put that we wanted the closed orbits to be non-degenerate. We could prove something much more general, and so we get a Weyl asymptotics for this massive situation. So I know I'm running out of time, and so I'm just going to make one more slide. So, you know, what is this kind of semi-classical problem? So propagation of light and particles at very high energy follow geodesics. They follow null geodesics. And that's why when we did the massless case, we end up with the dynamics on the space of null geodesics. But when we do semi-classical mass asymptotics, we're increasing the mass and the energy at the same time, and in a fixed ratio. So we end up working on a space of time-like massive geodesics. So be curious if any of you have ever seen anything like this before, or have ever heard of it in any physics text. So I think I'm going to stop here. So thanks very much for your attention.
Steve, thank you very much for a very interesting talk. Maybe I will stop the recording and we can proceed
Okay.
to the question and answer session, right?
Sure.